Today we're going to start with a recap of what we've been working on the last few days in terms of the exponential function and the logarithmic function being inverses of one another. So the first part of this lesson actually is a review of that, but our goal in the end is to know the laws of logarithmic functions and to be able to use those to simplify logarithmic expressions. All right, in terms of generic form, we know that our exponential functions look like this. We have y equals a b to the exponent of x. So just the b is getting the exponent of x. Our logarithmic function looks like this. It's y equals the log with a base of b of x. All right, so we have a couple of specific examples here. Y equals 2 to the x, and we've got y equals the log of x with a base of 2. So you can complete a table of values for those, knowing that one is the inverse of the other. So once you get your table of values for y equals 2 to the x, you know that you can just switch the roles of x and y, and that will give you the inverse of that. Okay, so your chart should look like the ones that I have here. Now, as far as our x-intercept goes, if you remember our exponential function, it is that growth, but it never actually touches the x-axis. There is no x-intercept for that one. Our y-intercept is visible on the table here. The y-intercept happens when x equals 0, so that is at 0, 1. Our domain, if we talk about our domain on this one, it's just going to be all real numbers. There's no restriction to it. When you sketch your function down below on the grid, you're going to remember that it goes on forever in both directions, to the left and to the right. Now your range will be all real numbers again, but such that our y is going to stay greater than 0. It stays positive there. So there is this thing called the horizontal asymptote, the HA. That stands for horizontal asymptote. And an asymptote is a line that your graph gets infinitely close to, but never actually touches or crosses. Okay, so this has a horizontal asymptote. When you graph it, it gets infinitely close to the x-axis, but never actually touches it or crosses it. So that x-axis is a horizontal line. It has a slope of 0 and a y-intercept of 0. So its equation is y equals 0. Now, with the exponential function, there is no vertical asymptote. There's no vertical line that your function gets infinitely close to but doesn't actually touch or cross over. So we'll fill in none for this. Now, we did talk about our exponential function and our logarithmic functions really just switch the roles of the x's and the y's. So the x of the exponential function became the y of the logarithmic function, and the y of the exponential became the x of the logarithmic. Now the same thing is true with all these characteristics down here. The x-intercept of our exponential was none. That means that this will have no y-intercept. The y-intercept was 0, 1. That means the x-intercept would be 1, 0. So do you see how those are switching? Our domain was all real numbers, and our range had to stay greater than 0. These are going to switch. The range will be all real numbers, where the domain for our logarithmic function will be all real numbers, but our x, such that our x has to stay greater than 0. Now, our exponential function had a horizontal asymptote of y equals 0. So these are just crisscrossing over. This will be a vertical asymptote for our logarithmic function of x equals 0. The equation of the vertical asymptote for exponential, there wasn't any. So with our logarithmic function, there's no horizontal asymptote. So on the next page, or well, for me the next page, but below you were to graph the two functions in two different colors. So I'm going to do this one in red, and I will do my logarithmic in green. All right, so if I plot these over here, my original exponential function is in red, 1, 2, 2, 4, 3 would be up at 8. -1 was a half, and then we've got a quarter. If we continued, that would be 1/8. So you can see we're going to get infinitely close to that x-axis, but in theory, we will never actually touch it or cross over it. Desmos, it's going to look like it's going to touch it, but that's just the resolution. It's not that it actually does touch. All right, and my other one, we had an x-intercept of 1. X is a half, we're down at -1. X is a quarter, we're down at -2. At 1/8, we're there. And then we also had a coordinate of, let's see what else we've got here. A 1, 2 becomes 2, 1. A 2, 4 becomes 4, 2. A 3, 8 becomes 8, 3. So we get this beautiful, whoops, beautiful logarithmic function that looks like that. So this is the log with a base of 2 of x. That's what this function is. I forgot my y equals here. Okay, and I've given you your scale and your labels on the x and the y axes there. So our two functions go on forever to the left and to the right for the red one, and on forever to the -infinity on y and +infinity on the x. And you can see we have a horizontal asymptote for the red graph, and we have a vertical asymptote, gets infinitely close to the y-axis but never actually touches or crosses it. Now the last part here says add the line y equals x to the graph. How does the exponential function compare to the inverse? Now we did a little bit of work with this the other day, and we know that if we were to draw that, whoops, let me see if I can get a actual vertical line or a straight line tool going on here. Nope. Good heavens. Usually it comes up really quick. And it doesn't seem to want to come up. Boy, that's like super crazy. Maybe it's because I'm on an angle. I don't know. Well, let's try from up here. Nope. All right. Well, if I had a ruler, if I would be able to actually draw a straight line, let me try that one more time. I would draw a straight line y equals x and put it, nope, put it through here. All right, that wasn't too bad for freehand. Okay, this is the line y equals x. And what we noticed last time is that the 1, the original function, if we reflected in that line y equals x, we get its inverse. So the inverse function would be the green graph. Continuing on here, since logarithmic function is the inverse of the exponential function, the same restrictions apply to the inverse as they do to the exponential function. So remember that the base of the exponential function is the same base of the logarithmic function. The y value of the exponential is the argument of the logarithm, and the exponent of the exponential is the y value of the logarithm. So we're going to talk a little bit about this. If we have y equals b to the x, and it's an increasing function, we know something's true about the value of the base. To be increasing, our base had to be greater than 1, okay, when that x is a positive exponent. If it's a decreasing function, what did we know was true about the value of the base this time? Right, our base had to be between 0 and 1. So that meant that to have exponential growth or decay, we couldn't have b equal to 1 because that was the straight horizontal line. We also can't have negatives because that doesn't give you a nice smooth whoosh curve. So those are things that we can't have. The same fact applies to the logarithmic function. Okay, the base can only have values that are either greater than 1 or between 0 and 1. If they're negative, not going to work. If they are equal to 1, doesn't work. So for the other thing we need to know or to remember, the exponential function y equals b to the x, the value of y, well, if we just look at the graph we just sketched, our exponential growth looks like this. If we graphed an exponential decay, it looks like that. Our y value is always positive. We always stay above the x-axis. That's why we had that restriction on our range of y being greater than 0. So the y is always positive. Similarly, so that since this becomes the argument, the value of x can only be positive. Okay, and especially for those people who are going on to 4U math, MHF 4U, this is going to be something that we need to play with over some time here. So I'm just going to fill in this last little bit here, if the function has exponential growth or decay. Okay, so you are going to use these properties to decide which of the following are undefined. So which of the following don't follow these rules? Put an X through them and circle the ones that do fit those facts. So if I was going through this question, I'd first look at the base values for my logarithms and see, do they either lie between 0 and 1, or are they bigger than 1? If that's true, then they are okay. If that's not true, right away I can put an X through them. The next thing I would look at is the ones that are left. If that argument is not a positive value, then I want to cross those ones out. Okay, check your work with mine and see if we agree. The rest will be on the next video.